Good morning, ladies and gentlemen. My name is Qingyan Chen. I am the director of the PolyU Academy for Interdisciplinary Research, or PAIR. So I'd like to take this opportunity to welcome all of you to join this PAIR Distinguished Lecture Series. Some of you might know that PAIR organizes such distinguished lectures from time to time. This is because we are working to address a number of societal challenges, such as climate change, energy, etc. And this is the topic of our lecture today. PAIR currently has 11 research institutes and 7 research centers. We try to work on 3 major areas, such as sustainable cities, advanced technologies, and health and well-being. So in these sustainable cities, energy is a very important component. We have the Open Research Foundation Research Institute for advanced energy, and this is a topic we've been working on that. And today, we are so happy to have Professor Chao-Yang from Penn State University to give a lecture on this topic. So Professor Chao-Yang has been very famous in working on the batteries for electric vehicles. So I was very fortunate to meet him in person a couple of years ago, when he was invited to give a lecture in the Hawkins lecture series at Purdue University. And I learned that he again was invited back to Purdue last year to give another lecture in the same series. It's a pretty rare case. The same lecturers was invited twice for the same series, which also indicate Professor Wang is a great contributor on the subject. So not only Professor Wang is outstanding, when I was at Purdue, I also served as the faculty research committee. And when I had the opportunity to recruit one of his former students, Professor Partha Makuzi, to be the Purdue faculty. So Professor Wang's contribution, not only from him personally, but also by his students and many other his colleagues. And we all know that electrical vehicle is an important solution to the energy crisis and the climate change. So I'm sure that Professor Wang's lecture will be very exciting, and I will have the opportunity to watch the recording after I return back to Hong Kong. So without further ado, I would like to pass this to Professor Lee, who will chair this lecture today.
Thank you, Professor Chen, for welcoming Professor Wang, welcoming you to this distinguished lecture. You may wonder why Professor Chen asked Dean of Humanities to serve as the chair for this PAIR distinguished lecture. I wanted to say that it gives me really great pleasure to introduce my former colleague from Penn State, where I was also working for more than a decade. And we got to know each other very well, although we did very different research. But I think my work and his work can be both qualified as interdisciplinary research. So I will give this very brief introduction to Professor Wang. Professor Wang is the William Diffendorfer Chair Professor of Mechanical Engineering and Professor of Chemical and Materials Science and Engineering at Penn State. His research interests include multi-phase transport, batteries, and fuel cells. He conducts fundamental and applied research on fuel cells and advanced batteries for electrical propulsion, stationary power generation, and portable electronics. So I will leave the details to Professor Wang to deliver, in his lecture about all the research findings to you. But at the Penn State, Professor Wang is the founding director of Electrochemical Engine Center, ECEC. It's very important to have a readable short form for center. So the ECEC under Professor Wang's leadership was the very first research in the innovation center in the world dedicated to batteries and the fuel cells for electrified transportation. ECEC provides a focal point at the Pennsylvania State University for multidisciplinary research on cutting-edge electrochemical power devices. In addition to ECEC, Professor Wang also contributes his expertise to other research institutes at Penn State, including the Institute of Energy and Environment and the Battery and Energy Storage Technology Center, which short form that's BEST. In fact, I was at the same time as the Associate Director for the Institute of Computation and Big Data. So you may be wondering why I became the Dean of Faculty of Humanities at the PolyU, given my also very highly interdisciplinary work. So Professor Wang's commitment to battery and fuel cells technology is widely recognized in the world. He holds over 140 patents. I'm actually applying for my first patent. And he has published over 230 journal articles and books, and 2 books. Professor Wang is the fellow of US National Academy of Inventors and the American Society of Mechanical Engineers, and the recipient of many awards, including the inaugural Research Excellency Award in Fuel Cells from the International Association of Hydrogen Energy. So without further ado, please join me in welcoming our distinguished speaker, Professor Wang. Professor Wang.
Thank you so much, Dean Lee, for the very kind introduction. Also, thank for the Professor Chen's video grading. Good morning, ladies and gentlemen. It's great for me to be here. Thank you so much for having me. I'm so happy to be here because I get to get chance to see old friends and meet new friends again. All right. I think the last time I was in Hong Kong probably was 10 years ago. But you know, the first time I was in Hong Kong was in '97. So it's been, you know, long time. It's also a great honor for me to deliver this pair lecture on battery fast charging for sustainable electrification. And I think, as most of you know, that electric vehicles, or so-called new energy vehicles, are becoming a booming industry. Okay? But in order to make the electric vehicles mainstream transportation, we still have to solve some basic, a few basic scientific and technological hurdles, and one of which is fast charging. So I hope we will touch upon this topic and share some of the latest research with you. Okay. Let me see if I probably, it's easier just to stand because I'm getting used to stand for presentation. To begin with, let's just take a look at economics of battery charging. Okay, this is something that we don't often read from articles or textbooks. Okay, but it's very important. Lay down the foundation for us to do meaningful research. Okay, so here, if you want to store electricity on vehicle, you basically have to pay $100 per kilowatt hour. This is a minimum, lowest price ever. Okay. However, if you want to refill 1 kilowatt hour electricity, it only costs 10 cents in US dollar. So the price gap between storing and refilling is 1,000 times. Okay. Now this price ratio in China is even more drastic. So today, I think you can pay 600 to 700 Chinese yuan to get 1 kilowatt hour battery on vehicle on board. But refilling 1 kilowatt hour costs only 30 cents Chinese yuan. Okay, so the price gap is 2,000 times. And that immediately tells you that storage actually is extremely expensive. And you don't want to store any extra energy than absolutely necessary. Okay, so in the medium, when you hear that long range vehicles, people want to overcome range anxiety, and you have to carry like 150 kilowatt hour big battery, this is going to cost you dearly. Okay, and so this very plain truth immediately tells us affordable EV basically means a small battery pack, but capable of 10-minute refill energy. So in other words, if you used up, the energy on board and you get refill 10 minutes, and then you can keep going, okay? So this concept can be easily illustrated by this schematic that I put it down there. And suppose today, if you want to drive or have a cruise range of 1,000 kilometers, then you need to use 150 kilowatt hour. So that's just energy balance. There's nothing you can do. It's a science, right? Now, to replace this 150 kilo by a 1/3 of the size, 50, you can get about 400 kilometers. The smaller, the lighter, and you get long range. So 400 kilometers. After you use this 50 kilowatt hour energy, you stop over, driver has to go to the restroom and check on the social media. 10 minutes, come back, your vehicle is ready to give you another 400 kilometer range, and so on. So if you get 2 times fast charge in 10 minutes, then you essentially also to get the same 150 kilowatt hour energy to use. Okay, so you get basically the same, but the benefit is tremendous. Number one, you only pay 1/3 of the price, right, as customers. This is great. Second, you only consume 1/3 of critical materials. All these batteries are made of critical materials such as cobalt, nickel, and so on. And many of those coming from countries where you have a little bit social problems, right? And the third, you basically produce only 1/3 of carbon emission from manufacturing those little batteries, right? You only use 50 kilowatt hour. So the benefits are tremendous if we can downsize. And the key to achieve this really is to have the fast charging capability, right? 10 minutes fast charge. So the newest concept in the electric vehicles and energy storage is basically called lean energy storage system, LESS, coupled with ubiquitous fast charging. Okay, less is more. And in this process, fast charging, as you can see, is an enabler of battery affordability and therefore EV affordability. Now, what about sustainability? Okay, sustainability 101 basically it's all about 3 R words: reduce, reuse, recycle. In the battery words, we hear to use, recycle all the time. But somehow we forget the first word, reduce, which is the first and most effective path to sustainability. And fast charging exactly is, enabling battery downsizing and therefore reducing the demand for critical materials and carbon emissions from manufacturing batteries. Okay, so here I give you a very simple math here. So if we take all the vehicle batteries from 150 kilowatt hour, downsize it to 50, that essentially save 100 kilowatt hour on each car if you scale to about 50 million cars by 2030. This is the number of cars we expect around the world every year, new cars. Then essentially you are removing 5 terawatt hour pressure out of this battery supply chain. Okay, in the last few years around the world, particularly in China, people always talk about expanding the size of the batteries. and scale up and so on, reaching several terawatt hours. But the science eventually will dictate to reduce the scale of batteries. And because efficiency and effectiveness is can be enabled by better science. Okay, we put out 2 years ago. We put out a commentary in the journal One Earth, and basically, advocating this approach, reduce and using the fast charging capability, and that immediately catch some reaction and impact from industry. And at that time, of course, we also experienced a critical material shortage. And today we have this gigantic effort to drive the cost down. So if you look at it, especially in China now, all the electric vehicles are in the price war. And all this will help us to do better science or taking better science-based approach, and therefore putting up a better vehicle or sustainability. Now, if you take the low cost and sustainability into account, then the conclusion is obvious. And that is, we probably just need a 50 kilowatt hour battery on board. That become a new norm for mass market electric vehicles. Okay. Now, if that's the case, then bring out another benefit, and that is to use lithium iron phosphate chemistry. Okay. And that chemistry has a little bit low energy density, but with that 50 kilowatt hour side, it can very nicely fit in any passenger car. And that chemistry itself brings low cost, abundant materials because it's based on iron. Okay, no nickel, no cobalt, and also high safety. And all these are very beautiful attributes for electric vehicle applications. And then if we make the LFP chemistry 10-minute fast rechargeable, now essentially we have no concern or worry about the range anxiety. Okay, so we did a 2-year study and then released the findings during the pandemic, published in Nature Energy in exactly 3 years ago, and immediately that changed the view of industry towards LFP, especially in the Western world. So before this landmark paper, Western world do not consider LFP viable at all for electric vehicle application. But after that, and also after a series of follow-up studies, and we basically convinced the whole industry go for LFPs. And today, actually a year ago, Tesla, as a pioneer in the industry, released in their what they call the master plan number 3, basically declare that 53 kilowatt hour battery will power 42 million EVs per year for the world. And that is also a very big statement. So you can see. Great, thank you. Laser. And the laser can be seen here, but cannot be seen. It's okay. All right, okay. Great, thank you. And our predictions this year will be even more dramatic. We believe LFP batteries will take up 90% of electric vehicle battery market, leaving those so-called ternary batteries as minority, okay, as in the niche market. Now, what about fast charging infrastructure? So if we are going to have a fast charging ecosystem, we need an infrastructure, okay? And our analysis is very surprising as well. And that is the infrastructure is already available, not only already available, but also largely underutilized. Why is that so? If you look at, this is, okay, I can just talk over. So if you look, we can take some analysis here. If you look at the Tesla supercharged network, which is available everywhere in China, around the world, it has each of them has 250 kilowatt. Okay, so essentially, if you do the energy balance, that is 5C charging at 50 kilowatt. In other words, every hour it can serve 5 EVs, right? Because each EV is 50 kilowatt hour, and 250 kilowatt running for 1 hour give you 250 kilowatt hour. So essentially, every station or every charger can give you can serve 5 vehicles, but today only 1 vehicle. All right, so that means it's only 20% utilization. Okay, and there's also a higher power chargers, DC chargers, like 350 kilowatt, and setting up around the world. And those even more powerful, they can serve 7 EVs per hour. Okay, today again, it's only 1 out of 7. And more recently, as part of this United States IRA, so-called Inflation Reduction Act, many companies, many automakers are setting up fast charging stations along the US highways, essentially distributed throughout the country. And GM alone is going to set up 2,000. Now, those 2,000 each of them has 350 kilowatt power. So if you just do a very simple math, assuming each of those chargers, okay, and running 12 hours per day, assuming it's, in full operation, 12 hours per day, and 1 week, it's already delivered 58.8 gigawatt hour energy. And that's already enough to charge 1.2 million EVs of 50 kilowatt hour each. Okay, so one company is already serving 1.2 million, right? And in China, the picture is even more dramatic. I think the latest news said that Huawei is going to set up 100,000 of those high power chargers. Okay, that's 50 times of this. That means 60 million EVs one company can serve. And today there's only about 10 million, even in China. So that means 1 out of the utilization is only 1/6. In other words, it's only 15, 16% or so. Okay, and that's only one company. And there are many companies wants to get into this field. So the charging infrastructure is largely underutilized. The problem is not charging stations, but fast charging batteries. The network, the bottleneck is over there. Okay, and even greater challenge is be able to deliver 10-minute fast charging batteries for all temperatures. And I think, as some of you already know, the battery charging capability deteriorate dramatically with decreasing temperature. Okay, so this is the map of average winter temperature in the United States. You can see 25 states have less than 0 degrees Celsius, 47 states less than 10 degrees. So low temperature in the winter is a commonplace. And this picture on the right, it basically shows you for a normal warm day, if a charge takes 22 minutes, and then during the cold day meaning freezing temperature, it becomes 50 minutes, all right? Double or triple the charging time, okay? Now, this problem of charging at a low temperature was totally exposed about 4 weeks ago in Chicago, okay? Chicago, at that time, the air temperature dropped to about -20 degrees Celsius. It's not the coldest, it's a very common one. But because of this, the electric vehicle charging station becomes scenes of desperation. So you basically have normal charging time is 45 minutes, now become 2 hours. And because one car is occupying a charger for 2 hours, other cars have to line up and they have to wait. They have to wait for 3 hours and total 5 hours. Think about it. If for driver to stick out in the, minus 20 degrees C air temperature for 5 hours. That's sometimes is a life-threatening condition, okay? And this desperation or scenes of desperation was basically broadcast by all TV stations in the United States, virtually all mainstream media. And this put a bad image for electric vehicles. And as a result, today, I think this year, the EV industry is going to decrease or scale back a little bit, at least in the United States, because we have not solved the problem of robust electric vehicles in the extremely cold, right? And people still think, you know, electric vehicle is toys. It's just for, you know, warm, nice, cozy conditions. Now, in terms of the science underlying this problem is a phenomenon called lithium plating. And this is what happened, you know, very large current charging basically generate a huge flux of lithium ions coming from cathode, and they have to insert it into the anode, graphite anode. And because of low temperature or because of other conditions, this high flux of ions don't have time to be nicely inserted into or intercalated into a graphite host. Rather, they start to deposit as a lithium metal on the surface, and this is called lithium plating. And that lithium metal on surface will cause two things. One is capacity fade, and second is safety hazard. Both are highly undesirable. So this lithium plating is most prone to occur under high charge rate or high current density, as you can imagine, and low temperatures I already explained. Also occurs for very high areal capacity or thick electrodes, and then thick electrodes just happen to be the key to make high energy density batteries or low cost batteries. Okay? So all those conditions happens in the EV industry, and the lithium plating occurs very dramatically in under those conditions. Okay, so how to solve this problem? And we've been working on this for, I think, more than 12 years or so. And our approach actually is a physics approach instead of chemistry. Okay, and that physics approach is called asymmetric temperature modulation. In other words, we will use the batteries as usual. So you discharge it at under all these normal conditions, ambient conditions. But anytime when you bring an empty battery in front of charger, we will do a preheating. Very rapidly heat up the battery to an elevated temperature for charging. And the elevated temperature give you enhanced kinetics, so very fast ion transport, and enhanced charge transfer kinetics. And therefore, you don't experience lithium plating, okay? But at the same time, we only use high temperature for charging, and during normal usage, we still enjoy the ambient temperature, which give you slow ACI layer growth, which is a degradation mechanism. So in other words, the key really is try to stay at a high temperature only for short, fast charge to avoid severe degradation due to high temperature. And in order to do so, we need a rapid preheating technique, right? And the heating time has to be less than 1 minute, right? Because your charging time is only 10 minutes. And that requires heating speed greater than 1 degree per second. And in the conventional battery systems where people use externally applied heating methods, the heating speed is only 0.5 degree per minute. And so that, you know, in order to raise the temperature, let's say from room temperature to 60 degrees Celsius for fast charging, heating alone will take more than 60 minutes, let alone fast charging. So total time is very long. So that obviously that's not going to work. And we invented a so-called self-heating structure back 7 years ago in a paper we published in Nature. And that gave us very fast heating rate, 100 degrees per minute or less than 30 seconds for preheating. And the structure is very simple, showing on the left over there, and as a yellow color here. Basically, it's you embedded a very thin nickel foil. It's about 10 micron nickel foil, showing as yellow with two ends. One end welded together with negative terminal, the other end coming out as a activation terminal. And then we place a switch between the positive and activation terminal. And once you turn the switch on, essentially you are using battery energy to preheat battery itself. So that's called self-heating, okay? The electric circuit diagram is showing over here. So this is battery is, simplified as a energy source plus internal resistance. And this nickel foil is basically a heating element, has a resistance. So you can bring this low temperature battery to a charger and connect it to a charger. Then once you turn the switch on, essentially the charging current will first go to the nickel foil and preheat the battery. And once it reaches a desirable battery, you turn the switch off, the same charge current will start to charge battery materials. So it's a very simple one-key operation, right? The result is very dramatic. But before I explain the result, let me also answer a question about the degradation at a high temperature, because our charging occurs at 60 and above temperatures. So if we take any kind of normal batteries like NMC, A11, or LFP batteries, put it in high temperature oven and doing cycling. So in this case, on the left, you see this basic 60 degrees Celsius. You do see a very dramatic degradation. So, about 1,000 hours, you get 80% capacity retention, meaning that you lose 20% capacity, okay? And that's end of life. But for our charging exercise, we only stay at this 60 degrees Celsius for 10 minutes every cycle, right? So 10 minutes, if you do 1,000 fast charging, you basically, the total time, lifetime is staying at a 60 degrees Celsius is only 167 hours, about 1 week. And 1,000 fast charging give you 200,000 miles. And that is way beyond any vehicle warranty, okay? So now what about 167 hours on this chart? So you basically see that's over there. So at that time, your degradation is still far away from 80% threshold, okay, far above. So that means as long as you control your time exposed at a high temperature, there's not much concern about degradation, okay? So this degradation at high temperature is strongly depending on time. Similarly for lithium iron phosphate, and we do even more severe high temperature testing. So we put it in 75 degrees C and 90 degrees C ovens, and we get those curves. And again, if you 167 hours is giving you around 5% capacity loss or 95% capacity retention. So over lifetime, it's a very minimum. Okay, so that address our concern about high temperature degradation. Now, once we remove the concern, then we can start to enjoy all the benefits of thermal stimulation, right? So, and lithium plating is mainly controlled by 3 processes. First one, the ion transport through the electrolyte into the negative electrode or the graphite electrode. And that process sometimes is very limiting. And then the second process is how this lithium ion is converted into atomic lithium at the graphite surface. And this is called charge transfer reaction. The third one is atomic lithium has to diffuse from the surface into the bulk of the particles. And this is called a solid state diffusion. All those 3 processes can be dramatically improved by higher temperature. So we did a property measurement versus temperature. And as you can see, this is the vertical axis is enhancement ratio. in reference to 20 degrees Celsius, and the horizontal axis is temperature. So going from 20 to 60 degrees Celsius, we basically enhance electrolyte conductivity by 2 times, lithium diffusivity in graphite by 6 times, charge transfer kinetics on the graphite by 12 times. What I mean in practice is by a single action of thermal stimulation, essentially I give you 3 new materials. A new electrolyte with doubling conductivity, a new graphite particle with 6 times diffusivity, a new surface of graphite, engineered surface of graphite with 12 times charge transfer kinetics. Okay, one action, I give you 3 new materials. And that is very unusual. If you take any chemical approach, you probably can influence one property or one material, that's all. Now, if you go from 20 to 90 degrees Celsius, the enhancement ratio is beyond the chart. Basically, you can do anything you want, okay? So that's the power of this thermal stimulation. Using that power and minimizing or suppressing degradation at a high temperature, now we can apply to all sorts of different batteries. And the first one I want to illustrate is this state-of-art NMC 811 graphite cell with the highest energy density possible today, 270 watt-hour per kg. And we can still do 4C fast charging. 4C basically means charging take 15 minutes up to 100%. If you do 80%, it's basically 12 minutes. Okay. And as you can see here, the red one is you can charge 4C charge it to 70% SOC. You can get almost 2,000 cycles, which is far beyond the DOE target illustrated by the dashed line here. And that only requires 500 cycles. And then if we use 4C charging to 75% SOC, then the beginning of life energy density is way higher. It's beyond 200 watt-hour per kg. In other words, this is how much energy you acquire after 12 minutes or so. And the cycle number now is beyond 1,000. So in a sense, we can achieve today, if you give me 10 minutes, I can give you 200 watt-hour per kg energy and 1,000 plus cycles, plus we do passive cooling. In other words, charging is occurring at a 65 or 60 degrees Celsius. And so heat dissipation is dramatic. And we really don't need any extra exotic liquid cooling and so on. So the cooling is passive, and that also gives us better safety aspect. Similar technique can be applied also to lithium iron phosphate graphite cell. In this case, we take a cell also with the highest energy density in this category, okay? And now we can do room temperature charging for 6C. 6C is 10 minutes to 100%, 8 minutes to 80% of electricity. And you can see that from room temperature, we can get more than, 2,500 cycles. And furthermore, I can take, about 12 minutes to do the charging from minus 60 degrees Celsius. Think about it. So ambient is minus 60. Nothing is working, but if you plug into our battery, you can still get battery charge to 80% in about 12 minutes. Okay, so that 12 minutes, we will give you 170 watt-hour per kg energy, more than 2,000 cycles, and passive cooling. Now, all those are basically sounds like a technological result, okay? But bearing inside is actually solving a science problem, okay? And that is the previous, I think I show you this image where the battery is basically unable to be charged in the extreme cold, okay? Now, in the extreme cold, it cannot be charged. This, if you think deeply, this is very much against science. Why is that so? I have a vehicle that is coming to a charger, let's say Tesla charger. It's ready to deliver 250 kilowatt. You get connected, but my vehicle, my battery say, no, I refuse to accept that electricity or that energy, right? It's against science. Even I take the simplest light bulb, connected to that charger, I would keep myself very comfortable inside the car, okay, without being frozen for 5 hours in minus 20 degrees Celsius. Even if I take just a very simple resistive heater, okay, which everyone has in your room and so on, and plug in, I keep myself warm, but only battery electric vehicles says, no, it's too cold, I refuse to accept energy when you need the energy most, right? So think about it. These are the things that I always try to stimulate my students. It's a think from the very basic level. Why the device, why is the electrochemical cell is designed in such a way that it refuels the energy when the energy is needed most, right? There's no other device in the world that behave like that. And now we put a resistor or heating element inside the electrochemical cell so that it can preheat and then it can promote electrochemical reaction, allow batteries to be charged, okay? So this is, once you understand the basic reason of a scientific problem, then you can come up with a solution very, very quickly and very easily. We did a demonstration 2 years ago now at the 2022 Winter Olympic in Beijing. It was very successful. So the technology was demonstrated over 400 cycles and basically bring all those athletes and coaches around between the game sites. Okay? And also last year we published, not last year, now it's 2020, we published a paper in Nature about fast charging. And 1 year later, the same technology and science went into production and it became product. Very quick. So 1 year from science to product. Think about it. Why is so quick? Because we follow this simple rule. Right? Simplicity is ultimate sophistication, especially if you want to build product. You got to have very simple technology, right? Now, let me switch the gear a little bit. So far I talked about how to get fast charging at room temperature, also at low temperature. But we also need fast charging for high temperature because the summers are getting hotter, right? I mean, we all experience. This is a map from 2 years ago, 2022. Think about it. California, air temperature is 47. In Spain, the air temperature is reaching like 50 degrees Celsius. So think about it. Air temperature is 50 degrees Celsius and pavement temperature is probably 60. And if you have an electric car parking on those streets, and those cars will be all cooked very quickly because current lithium-ion batteries are designed for 25 degrees Celsius, and they begin to degrade rapidly at a 35 degrees Celsius. And now you have 50 air temperature, 60 radiation temperature. So after 2 weeks, those batteries will degrade quickly. And also high temperature bring the danger or the risk of safety. So you can see all these things. I think just 2 or 3 days ago, there was an accident in Nanjing, right? Electric vehicle or electric bike accident, killing, I don't know, maybe, a dozen people. And those are all problems, safety. How do you do fast charging in high temperature environment and still with stability and safety? And that's a big topic. So here I use, basically a sketch to illustrate these things. Vertical axis is high temperature stability. This is something we must have. We cannot compromise. And horizontal axis is fast charging capability. This is desired. And if we go from that point now to the desired fast charging, the current method normally is using all these techniques like a nano-size particles, volatile, more volatile electrolyte, excessive liquid cooling. And those all leads to very high risk or very low stability. So for instance, a lot of people have proposed to use methyl formate, adding into the battery electrolyte to promote fast charging. Of course, it's highly volatile. Boiling point is 32 degrees Celsius. Fresh point is minus 33 degrees Celsius. So any of those will become basic vapor in the high temperature environment. So you basically achieve the fast charge at the expense of decreasing high temperature stability. And that leads to a fire. But what we need is more disruptive methods. We want to use stable materials to enhance stability. And then occasionally, if you do fast charging, we employ this ATM method. And also air cooling is better than liquid cooling in the hot environment. Okay? And along that line of thinking, the school of thought, we have investigated a number of new electrolyte, which will give us better stability at a high temperature. So for instance, the black line, the black dots, this is our current used in product, and which has about 2,000 hours cycling time at a 75 degrees Celsius. Okay? And this result was recently published in ACS Energy Letters. And we also have more viscous electrolyte, which we have not disclosed yet. And that will give us about 4,000 hours cycling time at 75 degrees Celsius. So that gives us much better stability. And if you use those highly stable electrolyte and then still do the elevated temperature charging, you only need about 333 hours for 2,000 cycles or 500,000 miles. And you can see the degradation is very minimum. Okay. And other research groups, including Professor Jeff Dang in Canada, is also actively working on more heat-tolerant materials. So in this case, they discovered something called DMO-HC solvent that has a boiling point of 220 degrees Celsius. Okay. And normally we use a linear carbonate that has about maybe 100 degrees Celsius boiling point. Okay. And very high viscosity, like honey, and very high temperature stable and safe, a little bit suffering the conductivity a little bit. And they can achieve 4,000 hours at 85 degrees Celsius. Okay. So that's even better, the higher temperature, longer time. So all these are great news for high temperature stability and safety always comes first. Okay? So just to quickly conclude and give you a little bit outlook, okay? Number one, and I hope I have convinced you the future belongs to this lean energy storage system or LESS coupled with ubiquitous fast charger. Okay? So analogy here is like you may need maybe 2 gallons of water every day, let's say, but you don't bring with you or carry with you 2 gallons water. You carry a liter water, and every building, I hope in PolyU, you can refill your water. Okay, that's the idea. So you need fast charging capability everywhere and anytime. And with that, you now have affordable and safe mobile energy. So in other words, the container you are taking around with you is going to be relatively small and safe and cheap. Okay, so EV in the future should carry just enough energy for a minimally convenient range. Like in China, you would talk about kilometers, 400 kilometers. That's it. Beyond which, basic customer, you can stop by to refill energy in 10 minutes, rather than try to load up huge battery packs in a vehicle. That's expensive. That's unsafe. So overall goal for us obviously is to reduce the cost, reduce the demand for raw materials, and increase sustainability, safety, and also charging experience. As a matter of fact, the bigger battery pack you carry, more difficult to do charging, right? At the same rate, you will need more or higher power. Okay? Less is more. That's the lesson we learned from whole research. Technologically, 10 to 15-minute charging of those highest energy density batteries is already ready. So waiting for engineering and industry implementation. And the new frontier for fast charging research is now the stability test. In other words, after you demonstrate you have the fast charging capability, you should put it into a 75 degrees Celsius oven and just to see how long it's going to hold out there. And if you don't do this test, that means it's not meant for the real world, okay? The real world will demand this kind of stability test. As a result, battery thermal management safety will see paradigm shifting technologies and implementation in the next 5 to 10 years. Smaller batteries with a higher temperature operation will a very completely different landscape for this thermal management. Okay? So just think about it. In the current practice, we basically doing the thermal management from maybe 30, 35 degrees Celsius battery and then dissipate heat to 25 degrees C temperature or ambient. So your delta T for thermal management is very minimal, 5 to 10 degrees Celsius. In the future, if we can operate the batteries at a 60, even 75 degrees Celsius, your delta T for thermal management is much, much greater, okay? 5 to 10 times greater. And that completely change your outlook and your landscape about the thermal management technologies. And we are in the midst of making this breakthrough change, so that you will see some paradigm shifting activities. So with that, I would like to thank you very much for your attention. And also, this is our Nittany Lion. So very proud to have been working at Penn State for over 27 years. I have many colleagues, great colleagues, that have moved away, but only I stayed in that little town for so long. I guess maybe I get too much sucked into this pursuing curiosity and forget about the outside the world. And so I thank you for also thank the Dean Lee for bring me out of that little town and see the whole world. And thank you so much.
Thank you, Professor Wang, for this wonderful presentation, this lecture. I think, no, you didn't got stuck in the little town because your work has significant and impactful implications for the society. I think Professor Wang's talk really showcases what the interdisciplinary research is about, from chemistry to physics to engineering and to society. As we can see today, how important it is to develop sustainable energy and the environment, and in the end, the sustainable society that we are facing all the challenges with. So I'm really very pleased to have Professor Wang today with us. I also noticed that we actually have more than 160 people online listening to your talk. And I already got quite a few questions from them. So I'm going to moderate some of the discussions and Q&A. I want to give the priority to colleagues in the room to ask questions first, and then I'll probably see what questions we have got from the online audience. So anyone has a question here for Professor Wang? If not, let me start with a very simple question as a moderator. So how long can you drive your car with the 2,000 cycles of charging in 10 minutes?
If your cruise range, let's say it depends on your battery size. Let's say take the smallest battery size. If your cruise range is 400 kilometers, right? So every cycle you get 400 kilometers and then times 2,000 cycles. That's 800,000 kilometers.
Oh, that's quite a lot. If we can do that in 10 to 15 minutes, that will, I think, solve a lot of problems. It will greatly encourage people's will to drive EVs for the future.
Exactly.
Okay, let's see. We have a question from an online audience. Your message on slide 3 suggests to me that what we need today is plug-in hybrids rather than pure BEVs. In the United States, this seems to be the message that the consumers are giving to the auto industry. Is that your impression too? Or do you think that BEVs with ultra-fast charging is the near-term and ultimate solution?
This is a great question. So I think what the person asking question is thinking about the so-called hybrid. Today, you probably have heard those hybrid, especially the range extenders, is very popular, probably more popular than BEVs or pure battery power electric vehicle. And the reason being, again, the batteries alone cannot cover all the different scenarios in the real world. And therefore, people try to use a range extender, a small engine, to supplement some of the functionality. Now, in my view, I think this is an interim solution. It's not ultimate. Ultimate solution is still going to pure electrification, okay? And in that sense, I could say the fast charging small battery actually is a range extender, in the sense that my fast charger on the road is off-board range extender, whereas on-board engine is on-board range extender, right? So now I get a range extender, which is off-board. I don't have to pay for it. It's on the road. When I need it, I stop by, get charged, extend the range for 400 kilometers in 10 minutes. That's very nice. I only pay, 30 cents Chinese yuan per kilowatt hour. Low cost, extremely low cost. I don't have liability for this range extender. It's off-board. I don't have to, pay for it. I don't have to maintain it, and so on. So this is, I think, it's ultimate solution. Now, of course, we, for this to happen, we need to have ubiquitous fast charging batteries employed in all vehicles. Okay, but that's getting there. Once they're getting there, the interim solution using internal combustion engine as an onboard range extender will disappear.
Okay, thank you, Professor Wang. Again, any other questions from the audience here? If not, there's another one from, please.
Okay, thank you, Professor Wang. Actually, I enjoyed your lecture so much that just like enjoying the talk show by Huang Xi. Okay, for the study here, the fast charging battery is more like to focus on the lithium battery, right? So currently, we also have the sodium battery. So this kind of fast charging also apply to the sodium one? That's the first question. The second one is the area is more focused on the all solid battery that will solve the safety issue. So in your opinion, which kind of battery is the most prospecting battery for the all solid one? Thank you.
So your question include two gigantic topics. Sodium battery is a big one, but I'm going to keep my answer very brief. You can talk for days just about sodium. I believe the sodium battery is a backup, okay? Because if you think about, again, from the very basic level, if you compare the sodium ion battery with the lithium iron phosphate battery, the difference, only advantage is you have more abundant sodium. Okay. Everything else is probably inferior to lithium iron phosphate, especially energy density. So the sodium battery will become important, only important in terms of the industry application. Okay. It's always important for research because at universities, we explore everything. We explore things that can maybe useful in 20, 50 years later. But for industry today, it will be only important if the sodium battery can demonstrate maybe 25% lower cost than lithium iron phosphate. If you cannot do that, no one is going to buy sodium battery. Okay. Now, today, in order to beat that 25% lower cost, it's a very tall order because lithium is theoretically is also abundant. You know, very large reserve in lithium on Earth. Today, the problem is the lithium carbonate price is very low, dropped from 600,000 yuan per ton to less than 100,000 ton per year. So today's price, even lithium iron phosphate sells only maybe 35 cents per watt hour. There's no way sodium battery can beat that kind of price. Only if the lithium resources, skyrocketing, or it become a so-called problem, then the sodium. So it's a backup. Right? Backup is, we all know backup. Huawei has a backup. 海思，我们叫中文叫什么？备胎，对吧？备胎 is very important, but only important for government and research institute to research. It's too expensive for companies to get engaged. That's number one. So all solid state battery also, all solid state battery. The first tenet of all solid state battery is improve the safety because we remove the fuel out of the batteries, okay? So for safety or the catching fire, if you look at the basic principle of combustion, you need three elements: fuel, oxidizer, and heat input. Okay. So in the case of solid oxide, people think, oh, what if I remove the fuel, which is flammable electrolyte, liquid electrolyte? Then I don't have the fire. But if you think again, you introduce another more reactive fuel into the system, which is the lithium metal. So you basically replace a less active fuel, which is electrolyte, by a more active fuel, which is a lithium metal. So the safety aspect of solid state battery, probably from science point of view, probably is a lot worse than the liquid system. We need to think about this. And if we want to solve this problem, we got to, design the research questions to overcome the fact that lithium metal is a very active fuel.
Thank you. We have two technical questions from online audiences. One is, why is nickel foil chosen as the heating element? Another one is, if we have battery swapping, may fast charging be much less necessary?
Okay, all right, I got it. So in our patents, we have over 100 different materials. We choose a nickel foil for a number of reasons. Number one is mechanical strength is better than, for example, aluminum foil. And number two, most importantly, nickel foil is also a great material to make what we call the temperature detector. So as a matter of fact, there's a device called resistance temperature detector, RTD, which is based on the linear relationship between the resistance and the temperature to back up the temperature. So essentially our nickel foil here is using as a heating element if the switch is on, but if the switch is off, basically it's inert and serve as internal temperature sensor. So it can actually give you early warning of safety or abuse conditions in that regard. Okay, so that's the answer to the first question. Second one is, yes, we can also use battery natural warm up as you operate the battery, especially in low temperature with very low efficiency. The battery will warm up, but it takes a long time to warm up. Take, let's say, 30 minutes to warm up. And also during this warm up process, if you prematurely charge the battery at high current, then you still cause lithium plating. Okay, so the difference between my approach and the natural warm up is we decouple the temperature from the lithium plating. In other words, we raise the temperature right away to a very high level to avoid any sort of possibility of lithium plating, and then do the lithium plating. On the other hand, if you say, okay, I start from low temperature, apply the high current, then waiting for this warm up to catch the threshold for lithium plating, at some point you may not catch, and you still make lithium plating, and that happens all the time. So, fast charging is a research topic for over 2 centuries, right? I mean, who does not want to have fast charging batteries? Time is money, as we always say. But the difficulty is great, and I think now we finally solve this puzzle.
Thank you. Any other questions from the audience here? Please.
It's very impressive presentation. I have mainly 2 questions. The first one is about, is there any potential damage that fast charging may bring to the batteries? And the second one is that I noticed that you mentioned the hydrogen fuel cell in one slide. So may I know your comment on this new energy device? These 2 questions.
The first one is more specific. So everything we do here is try to reduce the damage of fast charging a battery. That's why we do elevated temperature charging, which eliminates lithium plating so you don't have damage. But if you just apply high current to charge a normal battery, you do lots of damage. Okay? Second question is very broad, but fortunately, I have gone through this transition myself. So between 1998 and 2006, I think I was mainly involved in hydrogen fuel cell research. At that time was a very hot topic. And I was very, just like, started as a young assistant professor, and I was very excited because, think about a hydrogen fuel cell. The product is water, is deionized water, is water that we can sell from the grocery market. Very nice, beautiful. But as you dig into that fuel cell technology, you find more and more problems. You find more and more hurdles. Okay, so it's becoming becoming a technology we call the 5 year away, always 5 year away. So today we say, okay, 5 years later, we may have commercialization, which normally means you still need major science breakthrough to happen, okay? And that keep going, starting from 95 all the way to now, today, as you can see. Essentially 2 problems. I think one is the efficiency is still low. Second is the cost is prohibitively high. So I think hydrogen fuel cell, again, is a good topic for research. And I think if somebody can discover a breakthrough and then enable practical application in clean energy, that person will win Nobel Prize for sure. Breakthrough can happen tomorrow, can be, next year or 10 years or 50 years. We just don't know.
Thank you. Very interesting about the 5-year projection cycle. For those of you who watch local English channels, last night there was the replay of Back to the Future #2, and in there, the movie was made in, I think, in 1989. It was projecting 30 years later, so which is 2015. In the movie Back to the Future, they already at year 2015, there were flying vehicles all over, and today we don't see that. So you know, 30-year projection is not reliable at all, but maybe 5 years is better, and more reliable. Anyway, but changes are so fast. I think even 5 years is not a really good number because, for example, you know, the ChatGPT came out, right? 1.5 years ago. I think it shocked everybody. Nobody thought ChatGPT AI would be able to produce a human-like speech like we do, sometimes even better. And last week, Sora came out, you know, the video production also from OpenAI. And again, it shocked everybody because they can really produce very realistic videos now. The demonstration is only 1 minute, but I'm sure they have the technology to produce much longer videos. And that will lead a lot of people's job losses, I think, in the future. And again, the prediction was, according to an expert, they predict that only it will require at least 2 years to get to this technology. But now, only 1 year after the ChatGPT text-based chat bots came out, they now are able to give out full-length videos. So again, I think the fast pace of technology is beyond our imagination. So we don't know what 5 years will be like, but long-term projections are really unreliable. Anyway, this is my own projection of scientific advances in society. But I want to say, we have another question from you.
Thank you very much for your wonderful presentation. Oh, I have read your papers several years ago, and I noticed that after the high temperature charging process, there is also a 10 minutes cooling process. But I think if we add the charging time and the cooling time, it will be 20 minutes. I think this time is a little bit long. Do we have some fast cooling technologies to shorten this process? Thank you.
Okay, it's a good question. How do I go back to my slides? This one, yeah. So as you can see here, it's basically 4C charging and then immediately followed by C/3 discharge. There's no rest period there. And the discharge for C/3 discharge is designed to mimic highway driving, because C/3 means I discharge 100% energy in 3 hours, right? That's roughly right. If I, you know, have a fully charged battery and drive on highway 3 hours later, it's depleted. Now, the reason why you don't need cooling is, let's say, during 4C charging, you see the temperature is maintained pretty much constant. And then if you reduce the current from 4C to C/3, essentially reduce the current by 12 times. And in terms of internal heat generation, it reduced by 12 square. That's 144 times, right? So internal heat generation is shrink by 2 orders of magnitude, and external heat dissipation is still, you know, from 65 to ambient. So it's becoming, so the cooling on highway drive is, you know, after 8 minutes, it's already cooled down to 40 degrees Celsius. And now that answers your specific question, but in general, this is actually a good question. A lot of people are concerned about cooling, not necessarily heating, okay? But for anyone who is working on either heat transfer or, you know, we call it HVAC, or building things, cooling, heating and cooling is all relative, okay? So let me make an analogy. Batteries are like our human. It's the most comfortable if it's not too cold, if it's not too hot, right? Human too. In the winter, we need heating. In the summer, we need cooling because our most comfortable temperature is 35, 37 degrees Celsius. However, if I take a Dean Lee's, you know, very innovative approach, okay, someday I change the human gene to make human most comfortable temperature at 80 degrees Celsius. Then you can imagine we only need heating, we don't need cooling. even in the hottest, the humid summer here in Hong Kong, outside 40 degrees C, I need 80 degrees C temperature. I need to dress a little, thin coat, right? And all the air conditioning industry in the world disappear. So this is relative. If you operate, same thing. If you operate the batteries like a fuel cell, let's say, I think somebody had mentioned hydrogen fuel cell. Hydrogen fuel cell is operating temperature 80 degrees Celsius. And even there, we call it a low temperature fuel cell. We have Professor Ni, who is working on solid oxide fuel. That's a high temperature fuel cell. 80 degrees C, we never say this is a too high temperature. This is a low temperature, okay? But in batteries, if we change operating temperature from 25 today to 60 or to 80, that's still low temperature. There is no need for cooling at all.
Thank you. We have a question from online regarding speaking of highway, regarding the recent Chinese New Year, traffic jam on the highway. So I guess this is not unique to EV, but for all vehicles. So the question was does EV help with this type of sort of traffic? Huge traffic on the streets. If I'm driving an EV, do I have a disadvantage? In other words, to be stuck in a traffic jam?
Well, first of all, if you drive on highway, especially in the winter with jam, you need energy. You need access to energy, right? I mean, that's just the energy balance. You cannot create energy out of nothing. So you need energy. For that, if you drive EVs, you probably need very nice infrastructure, charging infrastructure along the highway at every rest areas and every 50 miles apart. You have the charging infrastructure, fast charging. You also need fast charging batteries so that every vehicle will drive in, take 10 minutes and leave, not occupying that spot for an hour or more than an hour, right? And that way you don't have the vehicles line up, everybody gets their energy. So I think that's basically the solution.
Right now, the infrastructure still favors the regular, gasoline, regular cars, non-EVs. I think in the US, it's clearly the case, but I'm not sure in Chinese highways whether there are more EV charging stations. But I think that the question really applies equally to EVs and non-EVs in terms of getting stuck in a traffic jam.
Yeah, right now the problem is twofold. Number one, it's a perception. People may feel that there's not enough charging stations, at least not as convenient as gas stations, right? But that picture is changing. I think even in China, there's so many companies that are involved now building the fast charging stations. Other than second asset problem is the currently available charging stations are largely underutilized. Efficiency is very low. Like in my talk, I give you an example of Tesla charging station. That's everywhere. It's in China, it's also everywhere. But that one charging station supposed to serve 5 vehicles per hour. Right now, it's only do 1 vehicle per hour. And that's our problem with battery engineers and scientists. So we need to have fast charging batteries which can take that high current from Tesla chargers. And right now, the utilization is barely 20% and below.
Several people ask you to comment on the research on battery safety during the fast charging process. Can you say a few words about the safety and compliance issues during fast charging for batteries?
Yeah, so safety in general, whether it's under fast charging or under normal usage, is always number one. Without safety, I don't think there is an industry or sustainable industry. So this aspect has to be taken very seriously. And right now, I feel, there's not enough attention given to safety even as an industry, because safety is something that is very difficult to quantify or very difficult to put a value on. Okay. Even if I make the safest batteries, and maybe, you know, it's $100 more expensive, and people don't buy it because safety has to be given. Your product has to be safe and without charging extra. And on the other hand, you see the trend of price war and so on. Immediately you can already know that quality is deteriorating and people are still taking shortcuts. You know, companies are taking shortcuts, which will reduce the safety aspect. And at some point, if a device or vehicle is cheap enough, essentially you take care of your own safety. That's an attitude, right? It's so cheap. I think that safety has to be overcome. And under fast charging conditions, safety is even more concerned because you apply very high current. And that's why in my talk or in the latest research, I believe it's not about just fast charging. It's about testing fast charging batteries in high temperatures under extreme conditions in order to ensure safety and stability. That's so put this fast charging battery in 75 degrees Celsius oven as a minimum, just to test. If you do the test, a lot of papers in the literature will disappear. For instance, people are, you know, propose to add methyl formate, which has a boiling point 32 degrees Celsius, or, you know, methyl acetate, 57 degrees Celsius. This is even more volatile than alcohol. So if you put all these batteries with those, you know, solvents in 75 degrees Celsius, immediately they will be, you know, screwed out and screened out, and that put us. I think the most important question is we have to pose right questions and then put all the resources and our young researchers' time, energy to address the right question rather than try to handle wrong questions. But that's a waste. So I think if once we know what are the standards, then the safety should be improved.
Thank you, Professor Wang. Because of time, you know, we still have many more questions online than we have time to answer. But because of time limit, we have to stop here. The final process for distinguished lecture today is a presentation of a souvenir to Professor Wang. On behalf of Director Chen, our pair, I present this plaque to you for your wonderful lecture to us, to the PolyU and the online community. Thank you.
Thank you very much. Thank you.